In our last video, we started applications of double integrals. We talked about area, and we found that doing areas by double integrals is not really an advantage. But when it came to volume to solids revolution, we saw a distinct advantage of the double integral over first year. First year, you had to talk about washers and or cylindrical shells. With the double integral, all you talk about is rings. And when you do that first integration, out comes the washers or out comes the cylindrical shells without you ever having to think about it. Today what I want to talk about is section 13.4, which brings back the application of fluid pressure that you had in first year, now to be attacked with double integrals rather than the definite integral first year. And again, we're going to find there is a distinct advantage of using the double integral. But let me refresh some of the ideas that we had in first year. When you go down into a fluid, so down here, there's a surface of fluid, and you go down into it, you talk about pressure. Okay? Pressure was supposed to be, it meant the magnitude, all right, pressure is not a vector, it's a scalar. It's the magnitude of the force due to the fluid at this point. And you developed a formula, which is rho, which is density of fluid, g, the acceleration due to gravity, and depth. That was the formula for pressure. And d must always be positive, because pressure is the magnitude of, therefore it must be positive. So whenever you put in for depth, it's got to be a positive entity. Then you considered problems like find might give you a thing like this. A plate submerged, and suppose this is the surface of the liquid. It's submerged in this fluid vertically. And you want to talk about the force on each side, right? On one side. So what you did at first year, suppose this is x is equal to g of y, and this is x is equal to h of y. What you did, you divided the plate into long, skinny, horizontal rectangles. And you said, all right, this is at position y, and its width is dy. You said, I'm going to calculate the force due to the fluid on that rectangle, then I'm going to add up my integration over all the rectangles for the plate. So you said, all right, basically all the points in this rectangle are at the same depth. So the pressure at every point is the same, and therefore I can get the force on that by multiplying pressure, rho g, depth, by area of a rectangle, which is its width, dy, multiplied by its length, which is h of y minus g of y. And for depth, it was this. So if that's my x system, then that depth is minus y. Right? You want this length, and the rule for length is upper 0 minus lower y. That was the force on this long, skinny rectangle. Then you added them all from, say here, C up to there, D. And that was fine, right? That was the force on that plate. But then I came along and I said, suppose this is the plate. So maybe this is y is equal to g of x, and this one is y is equal to h of x, and this is equal to a, and this is equal to b. And if I asked you to find the force on that plate, you couldn't do it. You can't take rectangles that go like this. Like here, you could take that kind of rectangle there, because all points in this rectangle are basically at the same depth. That is not true here. Different points in this rectangle, different depths. Therefore, different points subjected to different pressures. Therefore, you cannot calculate the force on that rectangle and then add by integration. So you were stymied. So first, your integration required that you had to use horizontal rectangles. Now let's think about double intervals. Suppose I've got this. I just give you a plate. There it is. Suppose the region inside of it is R. And I ask you, go find me the force due to fluid pressure on each side of that plate. You can say, well, here's what I'm going to do. I'm going to say, picture that as being a little piece of area at point XY. Right? All right. I'm going to calculate the force on that little piece of area. That means its area, which is dA, multiplied by the force. All right? Well, that's pressure. Multiplied not by force, by pressure. You can say, let's just let that be P. So pressure, rho G, and then a depth depending upon what the coordinate system is. But here it doesn't really matter. Right? So there's the force on that little piece of area. And then I add over them all to get the total force on the plate. All right? And if I, depends upon what I, well, let's take it. Let's take this one. Let's look at this baby here, which was so hard. In fact, you couldn't do it in first year. And let's do that one. Maybe we can do this one. Let's do this one first, then do that one. All right, and see if I use this idea. All right, on this problem, whether I get the thing I just unfortunately erased. All right, so force here is equal to, say, we're going to evaluate this double interval by using a double iterated interval, which means I'm going to go d, and I'll decide in a minute whether I want horizontal strips or vertical strips. I put in my pressure formula. Well, this is the pressure part. We had rho G, and we had minus Y. That's what we had a minute ago. All right. So we've now divided this thing up into d geometry of the rectangle like that. At position X and Y. We said, this is the force on that t geometry rectangle when I fill in this. But now I decide, am I going to choose vertical strips or horizontal? Answer, no way vertical, because they don't all start in the same place. Horizontal, yes, they'll start here. So we'll integrate with respect to X first. X, Y. Integrate, lower limit, where do all of the horizontal strips start? They all start here when X is equal to G of Y. Where do they all stop? H of Y. Now add another one. Where's the first one? C. Where's the last one? D. So there's what I get if I use a double iterated interval to solve that double interval. So if I do the first integration, I could pull out the rho, could pull out the G, could pull out the minus, and say C to D. Antiderivative of this with respect to X is XY. I pull out the minus. Between G of Y and H of Y, dy yet to come. So I'll get minus rho G. Integral C to D of Y. And then I plug in this guy and subtract. I go H of Y minus G of Y dy. And that's exactly the integral that I had sitting here a minute ago from first year that I erased. So I can handle, okay, the first integration in my double iterated interval leads me back to first year. Now let's talk this guy. If I want to do that guy, what am I going to say? Divide my plate of THUEG pieces at position X and Y of dimensions dy this way, dx that way. We'll calculate the force on this THUEG rectangle. That means pressure times area. Area, dd. Pressure. Pressure at points in this rectangle. Rho, G, and depth below the surface. That's minus Y. Right? So there's the force on that teensy-weensy rectangle due to the fluid, right? Now I add, what do I want? Vertical strips or horizontal? Definitely vertical. So I'm going to iterate in the y direction first. X later. Limits on the iteration. What does this tell me? Where do all of the vertical strips start? Answer, g of x. Where do they all stop? H of x. Now add over the strips. First one, A, last one, B. All right? And I proceed, all right? I integrate this with respect to y, and I get a y squared over 2. I put this in, and I put this in, and I proceed. So I've got a huge advantage then of using double integrals. I can use horizontal strips or vertical. But in first year, you had to use horizontal, long, skinny rectangles. So we see the advantage then of the double integral over the definite integral in first year. Well, let's do a specific example. Two of them I would like to do. First, I'm going to draw you a plate. Here's the surface of the food. And I've got a plate down here that goes like this. That is in there 1 meter. So this top point on this flat vertical plate is 1 meter down. This is 2 meters here. This is 3 meters here. And this is 6 meters here. It doesn't quite look to scale because that should kind of be the same as that, but forget that. All right. So objective then, find the force. Let's do water, okay? So this is water. Find the force due to the water on each side of this vertical plate submerged below the surface. So what are we going to do? We're going to divide this plate up into teensy-weensy rectangles at position x and y, of dimensions dy and dx. We are going to calculate the force on that teensy-weensy rectangle, and then we're going to add it by double iterated integral. All right, force on that rectangle is its area dd. Later, we'll decide y and x or x and y. I need to multiply that area by pressure. Pressure. Rho for water. That's 1,000. And g, and depth. Depth. Oh, I can't say that yet, even though I put an x and a y here. I haven't picked an x and a y coordinate system. So I've got to pick where to put the origin. And I guess there's a number of logical places. One would be here, one would be here, one would be here, one would be there, one would be there, or one would be there. Those to me are the logical places to choose your origin. Which one are you going to choose? I'll pause for a second for you to make your decision. You can put it anywhere you want, okay? You can put it, you want to put the origin over here? Be my guest. You're an idiot if you do, but you can do that if you want. I would suggest that since we need the equation of this line, sometime in this problem, I should pick an origin that facilitates the equation of that line. And to me, therefore, I would choose my origin right there. And choose my x-axis this way, and my y-axis that way. That would be my choice, so the equation of that line is as simple as possible. Since I need it, let's go get it now, so we won't get digressed later. All right. It goes through the origin, so it's a y equal mx. Right? If it shows up here, that's my origin. That would still be okay. You choose your origin up here, then it's going to be y equal mx plus b kind of thing. That's why I chose it here. All right, what's the slope? That's 3. This is 6, so therefore that's 3. And this is 2. So the slope then is 3/2. So there's the equation of that line. Now back to my integral. I'm calculating the force on that rectangle. I took its area. I now said multiply by pressure. Rho, G needed depth. How far, what is the depth of that rectangle below the surface of the fluid? That's that much right there. That's a length in the y direction. Well, length in that y direction, you take upper y minus lower y. What's y here? Answer, 4. And subtract y, 4 minus y. 4 minus y. There then is the depth. Now we add. Do we want to take vertical strips or horizontal? Obviously vertical. Horizontal got 2 kinds. So we'll take vertical strips. All right, that means we're going to integrate y first. Excellent. What does this limit tell me down here? Where all vertical strips start, they start here, where y is equal to -3. Where do they all stop? They stop here, when y is equal to 3x over 2. What is that on the board right now? On the board, that's the force due to the water pressure on this vertical strip. That's what that means, right? It's the force on that strip. Now we're going to add over all the strips, first to last. The first one is at x equal to 0, and the last one is at x equal to 2. So all I need to do is evaluate that. Now I'm going to do it, but I'm going to do it in a certain way that you probably are not likely to do at first, but I want to encourage you to consider this idea whenever you integrate. So let's pull out the 1000G. We'll have 0 to 2. And we have to integrate 4 minus 1. Now, what most of you would do would be to say 4y minus y squared over 2. Right? I want to encourage you, don't think that way. What I'm going to do is integrate this thing as a lump. I'm going to integrate, say, an antiderivative is 4 minus y squared. But I need a minus, and I need a half. That will differentiate to give me that. Right? So I'm going to pull out the minus 1 half, minus 500 over g, 500g. All right? So minus is out, the 2 is out, integral 0 to 2. Oh, I forgot to put here. I need to put here -3, and I need to put here 3x over 2. So I'm supposed to take that, put this into there, put that into there. So I would have then 4 minus 3x over 2 squared minus 4 plus 3 squared dx. All right? So now I'm going to integrate, again, now we're back to a first year definite integral. The second term, not a problem. The first term, instead of multiplying this out, I'm going to integrate it again as a lump. And write therefore, minus 500g, antiderivative, 4 minus 3x over 2, squared, integrated, it's going to get you a 3. I'm going to need a 1/3 to fix up that 3. I'm also going to need a 2 over a 3 to fix up the 3 over 2. And then I've got minus 49x, into which I'm going to plug 0 and 2. And I leave you then to plug in the 0 and the 2. Right? I recommend this idea of integrating as a lump can save you a lot of times in many problems. Try practicing it. Here, I don't think it's a huge advantage here. If I integrated this, then plugged in that, not a huge one, right? But I will get problems later where it will be a huge advantage to do what I'm trying to teach you to do here. So when you're done all this, then the final answer will be Newton's. So there's that example. Next one I would like to do is one from the exercises, because it brings something in that some people don't really realize at first, and I hate for you to see it on the exam. and get it wrong. And it also shows me something else that you should be thinking about. It's number 16 in the exercises. It says the following. You've got an oil can, which is in the form of a right circular cylinder, radius r, height h. The axis of the cylinder is horizontal, so the cylinder is horizontal. And this can is full of oil with density rho. And it asks you to find the force due to fluid pressure on each end. So I don't need to draw a cylinder. All I need to see is the end, which is a circle. And I think everybody would draw the circle and put a coordinate system at the center. So this is R, this is R. The H is really irrelevant. It doesn't matter how long the cylinder is. Realize that at first. Think about a dam on a lake. Does it matter how long the lake is for the force of the water in the dam? And the answer is no. Because once upon a time I thought I might have a brilliant idea. If you want to cut down the force on the dam, why don't you build a great big vertical plate and put it 1 meter away from the face of the dam? And therefore, the face of the dam would be a lot smaller now. And their answer is, no way. That was a silly idea. All right? Okay, back on track. So we want the force on here. Could we begin by saying that the force on the right half is the same as it is on the left half? And put in a 2 factor here and eliminate the left half and only do the right half. Could I say that the force on here is the same as the force on here and use a quadrupling factor? And the answer is no. These points are at bigger depths than those points, so the force down here is bigger than it is up there. All right, get that out of our minds. What are we going to do? We're going to divide this plate up into teensy-weensy rectangles, add point x and y, of dimensions dx and dy. We'll calculate the force on that little rectangle due to the fluid pressure, and then we'll add over all of the rectangles, okay? Force of the rectangle, area, dd. Must be multiplied by pressure. Pressure is rho g depth. Depth of this rectangle below the surface. Now, unfortunately, this is not like the last problem where the surface of the water was a horizontal thing. We're inside a tank. So what's the depth? Why I want to convince you, it's not that. It's that. Right? The depth of this rectangle, right, is that depth there, not that depth up there. Right? All right, so what do we need then? We need that. All right, that's a length in the y direction. Length in the y direction, upper y minus 1, r minus y. R minus y is the depth of that rectangle. The surface must be considered there, not here. Right? Okay. Now let's add. Adding. Do we want to choose vertical or do we want to choose horizontal? I think I would prefer to use horizontal. Because if I use verticals, they're going to go from this semicircle to that semicircle. If I choose horizontals, that's better. They go from the y-axis to the circle. All right. So we're going to go xy. All right. Integrate. Lower limit. Where do all the horizontal strips start? Answer, when x is 0. Where do they all stop? They stop at the circle, x squared, y squared, is equal to r squared. I'm going to solve that for x. Square root r squared minus y squared. That right there is the force on that horizontal strip. Now we add over all the strips, first to last. Last one down here minus r, first one up here at plus r. So there it is. All right? Now, what I'm going to do is not necessary, but it turns out to be definitely advantageous. I'm going to break this integral into two pieces. I'm going to break it into the integral of that, and then the integral of that. I'm going to write 2 integral minus r to r, 0, root of r squared minus y squared. And what's inside now is simply, I'm going to call it g to the r2, equal 2g and the rho and the r for that one. What's left is dx dy. So that's that. Then minus 2 rho g integral minus r is r, 0 square root r squared, y squared, y dx dy. All right. Look at that. Those. I want you to tell me how to evaluate the first one with no integration whatsoever. Tell me what the answer is with no integration at all. Think about what that double iterated integral represents. What are you doing? This is the area of a rectangle. And what does this do? Adds up all the areas of the rectangles. This, therefore, is the area of this semicircle. Well, I can do that. I don't need an integration to do that. 2 rho g r 1/2 pi r squared. There. That should be the value of this integral. Right? Now let's look at the other one. You're integrating y over this. Oh, you take the little dx dy here, and you multiply it by this y. For every little dy dx up there, there's a dy dx down here, and the y is the negative of. So what's the value of that integral? 0. I leave you to integrate it, but it's going to be 0. We don't need to integrate it to tell us that. Again, you've got an area here symmetric about the x-axis. You have in here an odd function of y. Even if this is a y cubed, I would still say the same thing. If you put an x in here, I will still say the same thing. All right? It's what y is that's important. It's an odd function, and you got symmetry around the x-axis. So the answer then is right here. Pi rho g r cubed. I'm going to write this back where it was a second ago. Rho g r pi r squared. So there's our answer, right? We know rho g. This is the area of the circle. The rho g, and what's r? Is r the depth of centroid of A below surface? Could we interpret the r that way? That the centroid was right here, and that depth right there, that's r. And this is not a peculiarity of this example. It is always true, right? That if you happen to know what the centroid of an area is, right, to find the force on it due to the pressure, take the rho, take the g, take the area, and multiply by the depth of the centroid below the surface, and you got the answer. So if I give you a rectangle down here, said, go find me the force, you simply say, multiply the area of the rectangle, multiply that depth, and throw in the rho, throw in a g, and out it will come. It's a nice little fact to know that idea, right? All right. That's it then for fluid pressure.